very briefly, biomass. It's here, it's used, there are great incentives for it. That's a 200 kilowatt biomass boiler. That's the sweet spot for the RHI. On the left is a wheelie bin, recycling bin. That collects ash. You can stick it on the rose garden. At the front on the right is the fuel feed mechanism. Typically, you have a fuel bunker in the ground above air. You have a big auger, or you have a big wheel turning it around, feeding it into an auger, which feeds it into the biomass boiler. Very agricultural, very Heath Robinson, but it works. But a lot of moving parts and a lot to look after.
They do take a lot of maintenance.
It goes back to old coal stoking. I think of sort of Casey Jones and stoking a steam engine. That's basically what it is. We're used to gas boilers that are on the wall. They fit in a kitchen cupboard, and you pay the gas bill, and they work.
What the school caretakers aren't used to.
Yes.
Go out there all the time.
These are fuel stores for wood chip. Typically, you want to have about 6 refills a year. Otherwise, it's like oil. You're getting a refill every 2 weeks. When you get snow, you're getting lorries up and down. You're having to deliver biomass or wood chip or wood pellet. One of the big problems with wood chip is moisture. If you get moisture into it, it starts to solidify. And actually, the moisture turns into steam, goes up the stack, and takes your energy away. So the optimum moisture content is 15%. You want to get deliveries of less than 25%. Anything more, you can start to lose 40% of your capacity. So a 200 kilowatt boiler suddenly becomes 120 kilowatts just by poor fuel stock. Just ideas of chipping machines, industrial chipping machines, and the scale of what you have to store to heat your property. And the industrial chipping machines, you can get machines, or the biggest machine in the UK chips 100 tons an hour. You basically throw trees into it. You see at the bottom the size of the tree there. Moving on to heat pumps. A heat pump is basically a compressor. Using the combined gas law, or a quirk of physics, when you compress a gas, the byproduct is heat. P1 V1 over T1 equals P2 V2 over T2. So you change the pressure, volume remains the same, temperature goes up. So we use a refrigerant that boils at anything above minus 20. So your low-grade heat, as long as it's above minus 20, you change your refrigerant from a liquid into a gas. You can then compress that gas. So at the bottom of the diagram, we see refrigerant or a cold water, ground temperature, air, whatever it might be, coming in at 0, goes out at minus 3. So we've now boiled our refrigerant, goes into the compressor. The CO2 compressors are higher, but the standard refrigerants that we use are R410A. We can achieve something like 20 bar, which is giving us temperatures of around 120 degrees centigrade. But this transfers to a heating system at about 65 degrees centigrade, which is the useful heat that we can generate. The higher the temperature that we harvest, a 1 degree raise in harvesting temperature is worth 2.5% in efficiency, and that works on the other side. A 1 degree drop in our heating temperature, then we get another 2.5% in efficiency. So we've absorbed our heat, we've compressed it, we've got high grade heat, we go through an expansion valve like an aerosol, and we change it from 30 bar into a vacuum. So it goes from a liquid back to a gas. And then the cycle starts again. That's a closed loop cycle. So 3 kilowatts of free energy from the ground, air, water, whatever it might be, 1 kilowatt of electricity produces 4 kilowatts of heat. And that gives a COP, or coefficient of performance, which is the heat pump's miles per gallon, of 4 to 1. Typical ways of harvesting the heat: horizontal collector in the ground, from groundwater, a borehole or a lake, or vertical closed loop. The best way to approach a building with a heat pump is to look at it holistically, to look at its heating, its cooling, how it's done, its seasonal, its occupancy, whatever machines are in there, ventilation and dehumidification. And all those things do actually happen in a domestic house as well. So something we spoke about earlier, simultaneous heating cooling. This is where you get the best out of a heat pump because you use both sides of the equation. Here's a building, boreholes in the ground. WP is the heat pump. We're now absorbing energy from the ground, upgrading it and using it to heat the building. So this heat pump's heating only. In this, we are using passive cooling. So the temperature in the ground is 12 degrees centigrade. We want to cool our building to 18 degrees centigrade. So we can passively circulate the water from the ground and take thermal mass out of the building. And that's effectively free cooling, or for the cost of a circulation pump. There's no compressor running. Now we're actively cooling. So the temperature in the ground is raised, so we've done more cooling. We're now actively having to run the compressor to cool it more. We've overheated the ground, so our load across the year is too high for the ground, so the rest of the energy is now being blown away in the air. Now this is where it gets interesting. We've got both heating and cooling, and in this case the heating load is greater than the cooling load, so we're rejecting heat into the ground, or energy rather. This case we're rejecting into the air. Now we're absorbing from the ground to heat the building, but we've both got heating and cooling. So if we look at a coefficient of performance, which is its efficiency of 4:1 on heating, 3 on cooling, we can get a seasonal performance factor of heating and cooling in excess of 6. So 1 kilowatt of electricity is going to produce 6 kilowatts of heat. So now they're massively more efficient. If we look at supermarkets, if you go into a Costco, you've got 500 kilowatts worth of refrigeration, and you've got 500 kilowatts of heating a big shed. In spring and autumn, the waste heat from the freezers can heat the building, but they never join them up. So you've got all this energy just being wasted. But there's a huge potential for supermarkets, and Sainsbury's have jumped on the bandwagon and started to do ground source heat pumps, but haven't gone and got the whole picture. There's a huge opportunity for them to bring their heating and cooling costs way down to almost half. The modular systems to bring it all together, to centralise what we're doing with it, do heating, cooling, free cooling and refrigeration. There is ground modelling. When you're doing ground source heat pumps, ground modelling is key. You need to look at what energy is in the ground. And it's natural energy, it's from rainwater, it's from groundwater, and it's from radiation from the sun. So collector array modelling is critical. You've got to plan your array for something like 25 years sustainability. So we have basically a finite element analysis program for doing modelling on the ground. So this is a 25 borehole array, looking at it in plan view. It's modelled over 20 years. So as it's getting blue is cold, red is hot, and you see it changing over time. And what you'll start to see is a plume, which is the net effect across a year starting to spread around the ground. So over a 25-year period, we are starting to warm this ground up because the cooling load is greater than the heating load. And this project was done for a big site within central London, where we had to put the boreholes in a grid fashion. There wasn't space to do it in a long line. So they get thermal interference with each other. If you watch the whole video, it's a bit like watching paint dry. But if we jump to the end, you can see the net effect of the plume there and the effect that it's had on the ground. And the reason it flows that way will be the flow of the groundwater in that direction. Now, if we look at it as an elevation, the same thing. So you see it's cooling, and we go back to heating, then we're cooling. And again, you can see the plume start to spread as the heating cooling cycles. If we jump to the end, you'll see the net effect. So that's chilling the ground all around. In Holland, legislation has said your net effect on the ground must be 0. So what you take out for heating, you must put back in cooling each year. In the UK, we don't have any of that legislation, but we're looking to Holland for what they're using. Now, they're looking at aquifer thermal energy storage. So you drill into the ground. Under London, there's a massive chalk aquifer, and the water levels are rising, so they're encouraging us to use it. So it's latent energy stored down there, and it's a phenomenal amount of energy. And if we can manage that, we can heat and cool buildings very effectively. So in this case, we've got heating, we've got cooling, emitting into a heating system, into an aquifer. So we are absorbing from the cold area, and we're dissipating heat in the other. So during the cooling cycle, we're dissipating heat in the aquifer and heating it up, as a conventional chiller would. Now in the heating cycle, we absorb that heat that we've just rejected, and we're now putting cold back into the ground. So the key here is to find a solution where we can, or size the system appropriately with sufficient backup. So maybe a conventional boiler to top up the heating and an air coil to get rid of excess heat. But we can use the natural energy within the ground sustainably year on year for doing both heating and cooling within a property or a process. This is an aquifer model, so that shows you the two aquifers, one which we're heating and one which we're cooling. So at the end of the summer, we've rejected a lot of heat, so we've heated up one aquifer. This is in the peak of winter, we've chilled down a whole area, and we're starting to interfere with the other aquifer. So we're absorbing heat and moving heat between the two and using it naturally within the building. Another way of increasing the performance of a heat pump is to look at other collectors. Solar thermal. Solar thermal panels, great for heating hot water. They're probably about 40% of our domestic hot water need. If we put that solar thermal energy into the ground, we can absorb 4 times as much as we can for hot water, and we can store that as a low-grade heat within the ground, which would otherwise go to waste. Asphalt solar collectors, tennis courts, they're black, they absorb heat. They can be up to 17 degrees C underneath with the sunshine. All that heat is useful to a heat pump. You can also maintain it at a slightly hotter temperature as a defrost for a car park or something like that. A thermal bank, burying pipes within the shadow of a building so there's neither sun on it nor rain, and we can store energy under there. Add that with a heat pump and you've got interseasonal heat transfer. So this shows you a building, pipes underneath storing the heat. We're absorbing solar gain from outside and water. We're absorbing waste energy from the building. And then in the winter, we're putting it all back again to heat it. And that can have a huge beneficial effect on a building and its running costs. So there's examples of car parks with collectors buried underneath them. And the red tubes are a thermal bank going underneath the building to capture the heat and store the heat in the shadow of the building. So I just thought I'd throw this in the end. This is what I'm doing this week. Woburn Abbey, Woburn Safari Park you may have heard of, goes back to your question about historical buildings. Woburn Abbey is a Grade 1 listed star building. We can't touch the inside of it. But we're heating, they've got a heating bill of £47,000 a year on mains gas, which equates to nearly 1 megawatt hour thermal to heat that building. We're putting 360 kilowatts worth of heat pump in there, and we're burying in the parkland a 24-kilometre ground collector to absorb energy. And that will be sustainable year on year to heat that building to the temperature of 21 degrees, which is what they require. That actually kicked off this week. 24 kilometres worth of trenching is going to take about 2 months, burying that pipe in the ground.
Is it slinky? How deep is it?
Because it's parkland, we would normally go a metre down. Frost penetrates in the UK about 300 mil. Pipe absorbs from 500 mil around it. So if we go a metre down, we're absorbing away from the frost line. Because it's in parkland, they put marquees on it. They have a tiger moth festival which lands on there. We've gone 1.4 metres down to get away from the marquee stakes, basically. But yes, there's a huge amount of thermal mass in there. And we avoided the lakes. The low-hanging fruit there would be the lakes. But we did a hydrological study on the lakes. They're man-made, they're spring-fed, and they're not sustainable, and there's not enough energy in there. We could have developed that lake, but the Duke of Bedford looks out on it. It's his vista, and he enjoys seeing the deer watering and drinking there and swimming in there in the summer. So we couldn't touch it, so we didn't. But it's an interesting project and quite a challenging one. Next to the house, we're going through an area called the Monk's Burial Ground. We had to go for listed property approval here. When they heard Monk's Burial Ground, they jumped up and down. We want radar scans of the area. We need to find this monk where he is. It was about the 5th Duke dog. It was called Monk. He got buried there. But listed property said, no, it's the Monk's Burial Ground. We're going to check it all out. They also thought that the original abbey was built on the ground where we are putting our trenches. So we had to do a radar scan of there to check that out as well. So from agreeing to go ahead, it's probably 14 months before we've been allowed to actually touch the ground, to go through all the bureaucratic processes of planning permission, English heritage, listed properties, etc., to get to where we are. Anyway, I just thought I'd throw that in for interest. And then, thank you for inviting me to talk. That's me. Also call myself an eco-warrior from time in Africa. Any other questions? Yeah.
On the issue of seasonal heat transfer, which company was it who did that? Was that ISAC?
Yes.
Okay.
They're promoting that.
Okay.
It's various other people have done it. Holland, they've been doing it. And dumping solar thermal has been an obvious way to do it of recent, but it gains no benefit from the RHI. I did a project in Wakefield actually, or a feasibility for somewhere. It was one of the housing associations, got a block of 96 flats. It's east-west, a lovely flat roof. I worked out that if we could put 120 square metres worth of solar thermal on there, we could reduce the borehole drilling by 25%. But the economics of that, just one paid for the other. So it was neither here nor there in reality. Any other questions for anyone?
I want to go back to this, to the discussions about the Renewable Heating Initiative and the impact of shale gas. Because in principle there shouldn't be one, should there? Because you should use the shale gas to generate electricity, send electricity to everybody's house, and they'll still use a heat pump.
Yes, but the government's paying out RHI money. They've just woken up to it. I don't know. Mutterings from ministers in DEC in December were their 2050 policy of putting domestic heating onto electricity is going to change. We wait to hear what that is. But they're all getting very excited about fracking and shale gas. They've seen America. Allegedly, it's turned around the American economy. Who knows? America is a lot less dense populated than we are. Isn't Leicester the earthquake capital of the UK? We'll see.
Yeah, my understanding was that DEC now had somebody who understood thermodynamics. It sounds as though they don't.
I'm not sure they got someone who understands heat pumps either, but anyway. Yes?
What are your thoughts on the environmental effects of fracking?
Fracking's a different debate. I don't know enough about it. Only what I've read. Probably the environmental effects, if you look at carbon, it's good. Gas is a clean gas. If you look at aquifers and things like that and the damage they're going to do down there, I almost think they shouldn't touch it and look for alternative methods, really. We don't know what we're playing with. I mean, you look at the oil drillers, they're used to going 2 kilometres down and 3 kilometres left. They can pretty much direct a drill wherever they want to go. But the concept of pumping water down there at high pressure, it just seems an overly energy-intensive method of giving out a bit of gas. In the 70s, when we first discovered North Sea oil and gas, 1 barrel of oil generated 70 barrels. Sorry, 1 barrel of energy generated 70 barrels of energy. Now it's 1 to 10. So that the cost of exploration, or there's more money available for exploration. So it's the coal tars in Canada is the same. Separating oil from the coal tar sands up there has suddenly become viable. All exploration, talking to a colleague a year or so ago, has been done at $120 a barrel. I don't know what the price is today, but it's slightly under that. So their oil price will go up, and then more exploration is going to become possible and viable. That's the economic argument. Environmentally, I don't know. The thought of high pressures under the ground worries me, I think. Yeah.
Just
Question.
on that point, the Energy Society will be holding a panel debate on fracking in the next couple of months. It's scheduled to be at the end of March. We're confirming the panelists. So hopefully that should answer some of your questions.
Another question?
What is your take on passive housing? Do you think that they're excessively over-engineered, especially in regions with high amplitudes of temperatures?
I'm not sure I've seen a passive house that actually works as passive. Are they over-engineered? It's the law of diminishing returns. You can spend 10% of your money hitting 80% of the solution, and the last 20% cost you 3 times as much. Yeah, it's great for any industry to experiment and drive excellence and then bring learning back from that into standard housing stock. there's so much more. I mean, the problem with the UK housing stock is it's so decrepit and old, and we've got solid walls and things like that. Passive house only affects a small proportion of the housing stock. Passive house is a good idea, but developers won't go for it because it kills their profit. And actually, Code for Sustainable Homes, I learnt last year, the end of last year, is being watered down. So government has put policy in place to get developers to build houses which use less energy. And now they decided to water it down because all the developers are saying we're not making enough profit. Does that answer your question? Yes.
Related to that, how much of a role do you think that increasing the energy efficiency of buildings will play in offsetting the energy that we need?
I shall answer that by saying energy is too cheap. And that's actually the cost of energy will drive efficiency. It really is as simple as that. The more energy costs, the more we will be forced to make our homes efficient.
Do you think that's a route to go down?
It's...
Maybe not.
Okay, my personal situation, I bought a house which was built in 1863. It's got solid brick walls, single glazing. I've lined the inside of those walls I want my running costs. I intend to live there for the next 20 years. I want my running costs to be low. My neighbours haven't, and they freeze. And you watch the condensation on the inside of the windows. Invited them round for drinks before Christmas. They came round in fleeces and layers and everything. We were sat there in shirts and trousers, and our heating bill's less than theirs. So it's going to be energy costs that's going to drive it. But the right way to go is insulation. Stop the heat loss. But with insulation comes problems of ventilation. Sweden or Scandinavia found it. They insulated their buildings, made them airtight, then got sick building syndrome. So then they lead us in mechanical ventilation in a big way. And to go back to the passive house, some of the mechanical ventilation that comes out of Scandinavia is an air-to-air heat pump. So it's 140% efficient down to -10. So a little 500 watt compressor is generating enough heat to overcome the ventilation loss plus some. So heating systems don't kick in till it's about 0. So they're very, very efficient. And I don't know how far away we are from that in our housing stock, but the developers are nowhere near it. It costs too much. Any other questions? One more?
Very, very quick one. Is that thermal bank idea suitable for, say, airports for de-icing runways in the winter? Would that be something?
There's no reason why not, because to de-ice a runway, you only need a low-grade temperature. You don't need to run a boiler. If you could store, there's no reason why not. It's the capital cost of doing it. But in somewhere like Canada and North America, where they get more extreme temperatures, then it makes more sense. Over here, we get, a couple of days a year with the airport shut. It causes chaos, but it really isn't very long. Any other questions? Well, thank you very much.
Thank you.